Okay, good morning, everyone. We'll get started, please, this morning. So as I alluded to the last little bit, we're still in this course talking about tension members. I swear it's up there somewhere. We've been talking about tension members for quite some time. I swear Wednesday is the last time we'll talk about tension members, but we're still talking about them today. The reason we're still talking about them today is we've discussed already these limit states: gross section yielding, block shear failure, and net section fracture, and also some serviceability limit states in lecture 16. Today, the last couple days, we've been focusing more on welding tension member connections. So we talked about these expressions and how they might be applied for bolted connections. We are also aware that from time to time we might weld instead of bolt. Sometimes it's a bit more useful, especially in the field if you're trying to accommodate tolerances or pre-tension something. It's sometimes easier to weld these things. And so it's not really that different for block shear, and I may or may not discuss it a whole lot, the block shear component, if I can get my pencil working today. But what we are going to focus on today is how this ANE expression works when we have welded connections. When we had bolted connections, we tuck away cross-sectional area to make the bolt holes, to make the bolts fit. That reduced the area and tension at the connection. And when we only connected some of the components, like one leg of an angle, for example, we started to have to consider the effective area of the net section, the ANE term. So today we're going to talk about how this stuff works for welded connections for our tension members. And we're going to, at some point today, talk about this example where we had the welded tension member at the other end in that example building on the north side here. And basically what we had, and we looked at this example the other day, at the end of lecture on Friday, we calculated the resistance of these fillet welds in shear. And so today we're going to look at the effects of those fillet welds and their position on the tension members and how they might fail in the net section. We're also going to look at a special case today. We haven't talked very much about HSS as they pertain to tension members. And for the most part, it's because we don't really bolt them. They're kind of hard to bolt. They're tubes. You can't really bolt HSS sections very well. And the preference is to weld them. And so we'll talk about what this welded connection tends to look like, if I can get this damn pencil ever to work. And maybe if I exit out of this, and I'm going to try this. I'm going to close this. This is what I did the other day. I'm going to get too annoyed. Let's try this one more time. And let's get this shared. Let's see if that works. Oh, there we go. Pencil's starting to work now. So we're going to talk about this special case today and how we can figure out what the effective net area is going to look like so we can do our net section fracture calculations for these kinds of situations as well. Basically, after this morning, you should be able to describe the transfer of stresses from tension members to the gusset plate through the welded segments. So we're going to look at the effects of the location of the welds on the tension member now, calculate the shear leg factor for net effective area for typical welded tension members. And we're going to see we're not usually dealing too often with a shear leg factor. We're going to deal with a shear leg factor for HSS connections. We're going to be directly calculating the net effective area for most other situations. But from the effective net area, we can back calculate a shear leg factor just for comparison purposes with bolted connections. And similarly, we're going to look at calculating the shear leg factor for net effective area for welded slotted HSS connections, which are a special case. Most situations we can do the same kinds of calculations, get net effective area. Until we start dealing with HSS, it's a little bit different. Does anyone have any questions about these three things and why they might be important to us before we continue on with the rest of the stuff this morning? Okay. Now that I've got pull everywhere under control here, this one should perhaps give you a slight memory to a similar question back in lecture 13 when we looked at net effective area for bolted connections. Now we're looking at net effective area for welded connections. And this is just a simple flat bar. It's welded in three different orientations. One has a weld across the butt end of the plate to the gusset plate. In the other one, it's got the two longitudinal welds. And in the third, it's got a single longitudinal weld. I'm wondering if you could identify which of these three arrangements actually results in the largest effective area of the tension member being effective at resisting stresses. So basically of these three, which of these three do you think has the largest percentage of the cross-sectional area of the tension member being effective at resisting net section fracture. Is it locked or is it open for? Okay, it's open. All right, so we've got the usual 16 or so participants here in the poll this morning. This is one of my favorite questions because it's kind of interesting and it's fun to get something wrong and learn why it is that it's wrong and kind of figure out what's going on. So almost always people in this class focus on the middle example. And I would say 75% of the people answer middle one. The middle one looks perhaps intuitively right because you've got a lot of weld, it's on both sides, it's well balanced. The right answer is actually the first one here. And we'll talk about why that is, but I'm curious if anyone picked that one, if you want to perhaps share, if you feel comfortable sharing why you picked that first one. What makes it seem that that one would have a larger percent area effective?
I just figured that in tension it's going to be pulling, so if it's directly associated with the one side that's pulling, meanwhile the sides are going to be more so friction-based in a way. That was at least my thought.
I think you're getting 85% of it there. Does anyone else want to share something as well? So basically, to Chandler's point, pretty much, like basically what's going on here is we want the entire width of the plate to be effective in tension. Right? That's the goal here. And the only one of these welds that actually transfers the stress across the complete width is this one. Right? The stresses have to come down through the weld at the end of the tension member here. And so in terms of the proportion of the width, this is connecting the full width of the plate. Right? And so it's going to basically one for one along the length of the weld transfer the stresses into the width of the plate. And so in cases like this where we have this transverse weld, right, a load that's perpendicular to the applied force along the width of the plate, all of that area is going to be effective in tension. Now usually we don't just do that. We might also have some other welds here because it's not the best practice to just do that kind of thing. Sometimes we might look at a situation like this, and it's actually pretty common to have two longitudinal welds because it's more ductile, it stretches more before they fail, and it's usually easier to do that kind of weld. But basically the stresses are getting transferred through the edges, right? The stresses start to get transferred here somewhere. From the tips of the welds, they have to start making their way, the stresses, to the critical net section, and the shorter those welds are, the less percentage area we're going to have effective in tension. The one on the right-hand side is an even worse case, and we'll talk about how we calculate the net effective area associated with each of these. So in CSAS 16, we have clause 12.3.3. 12.3 deals with net effective area, and 3.3 deals with shear lag and net effective area specifically for welded components. And basically what it tells us is we take the net effective area for welded members, which are usually flat bars, angles, and channels for the most part. And we add together the different net effective areas based on how those different components are connected to the gusset plate. Basically what it's telling us here is if we have part of the plate that is welded along the full width by transverse weld, we're going to get the net effective area associated with that, and that's going to be 100% of that component. But we're also going to have situations where some of the components or some of the plates of the cross-section are connected along just two parallel edges, and some where the net effective area is connected just along one parallel edge. Okay, so I'll talk about what each of these pieces mean here and how they apply to the flat bar configurations we just looked at. And then we'll start to put these pieces together for shapes like angles and channels and see how we tend to treat those individual shapes. So what this AN1 term is basically is if we ever have a part of a plate that's connected by a transverse weld, like that first part of the pull everywhere problem here, basically as long as there's this transverse weld along the back edge of the plate, all of the stress is going to get transferred to that tension member because it's completely connected across the width of the plate. And so these stresses are more or less going to make their way to the weld, to the effective net section. And so by the time the stresses get to the end of the welds where the tension member is likely to fracture, we're going to have 100% of that area effective in tension. And basically what this means is that the shear lag factor is simply equal to 1, right? There's no reduction in the effective area associated with this kind of situation. Does anyone have any questions about this scenario before we talk about the next one? It's quite common to not weld the end of the tension member and just use 2 longitudinal welds instead. And that's perfectly fine, and it's common practice. The welds is actually probably the best way to do your welding, but that has some implications on how much of the cross-section at the ends of the welds is going to be effective in carrying that tensile stress. As you might expect, it's proportional to the length. If you've got really, really, really short welds, like if you only have welds something like this and like this, there's not very much space for those welds to transfer the stress into the tension member, and so the net effective area associated with really short welds tends to be quite small. And basically we'll see here when the width of the plate, right, W, is longer than the length of the welds, we're only getting 75% of the length of the weld times the thickness. And so L is the length of, not the total length, this is not LW, the length of all of the welds added together, it's the length of the welded connection here. And so basically we take 75% of L times the thickness of the plate, and that gives us the effective net area. And so basically what that means is that the shear lag factor is basically 0.75 L over W, and it depends on the length and the width of the plate. As the welds get longer, all the way up to the fact that if we have welds that are twice as long as the width of the plate, we have, it's basically WT, right? I don't even know why they write 1.00 WT. To me, that seems a little bit weird to write 1 WT. But basically that implies you get the full net effective section, effective in tension there. And so as the length of the welds gets longer and longer and longer, we get more of the effective section carrying the tensile stresses. And if you're in between those two cases, where the length of the welds is something between the width of the plate and twice the width of the plate, then we have something in between. We get half of the area of the plate plus 25% of L times T. And in this case, basically, I guess you could say the shear lag factor would be something like 0.5 W plus 0.25 L over W or something like that. And you could calculate it. That's going to be between these two other ones. Okay, so what I'm getting at here is whenever you don't have that transverse weld, it takes time and space for these welds to transfer stresses into the effective net section, and we only get to take some of this area at the width of the plate as being effective in tension. The longer the welds are, the more area we get effective in tension. Okay, does anyone have any questions about this scenario before we talk about the last one? The last one is not something you would ever do for a flat bar by itself. We'll see how this applies in a second. But if you have a flat bar or a component of a cross-section that's only connected by a single longitudinal weld, then we basically have a couple different situations here. For quite long welds, so if L is greater than W, we've seen a factor that looks something like this before when we talked about bolted tension members. This is the shear lag factor that I showed in lecture, whatever it was, 12 or 13, 1 minus x bar over L. X bar is the distance of the centroid of the section away from the weld. And so the weld is here, the centroid is here, and so the perpendicular distance between the weld and the centroid here is x bar. And so for longer welds, we can take a shear lag factor basically of 1 minus x bar over L times WT. And for shorter welds, we just get half of LT. And I'm not super sure where this particular term comes from, but normally what would happen is they'd do some testing. Someone would pull apart the cross-section in something that looks like this and basically try and figure out what would make sense there. I would say, as a rule of thumb, I would avoid this case. This just seems a little bit silly to me, but in any case, we'll see how this applies in different situations. Again, you would never just have a flat bar as a tension member welded by one longitudinal weld. That would be silly. But we'll see in a second how we can apply this case in other situations. Does anyone have any questions about this scenario or any of the other two before we continue on? Okay. So we have a situation where we have all of the bar effective if we have a transverse weld. We have a situation where we have some of the flat bar effective if we have two longitudinal welds. And if we have long enough welds, we can get the full effective section. And we've got a situation where we have one longitudinal weld, basically never going to get the full net effective section, but we can still get some of that section effective in tension. These are the three terms, AN1, AN2, and AN3. And the questions you probably have are, how do we take AN1 and add it to AN2? Is it something to do with these longitudinal welds being present with the transverse weld? The answer to that question is no. But what this expression AN1, AN2, AN3 is supposed to apply to is cross-sectional components or cross-sections that have different kinds of plates that make up the shape of the cross-section. And we're basically going to see that we can treat the different components of the cross-section as these different flat bars to add up the total effective area in those situations. For example, if we had an angle that was welded on two sides, then we would basically have here AN1, which would be associated with this leg. This leg happens to have a transverse weld along the entire width of that leg. And so in that case, for that leg and that leg only, we would have AN1, which is equal to WT here. Right? So if we have the long leg connected, then W, the width of that leg, is equal to D. If we have the short leg connected, it's B. Not super important which those are. What's important is that we have one component of this angle that is basically a flat bar with a transverse weld on it. So basically this one corresponds to an AN1. We might calculate for that part. And then this outstanding leg here would be an AN3. This is basically a flat bar that is connected just by one longitudinal weld on the edge. Right? So we can basically treat it as this part. And so we can say we have AN1 plus AN3. And in this case, we don't have any specific AN2s. And so AN2 might just be 0 because we don't have any one component of this cross-section connected by two longitudinal welds only. We've got one that has a transverse weld, one that has a single longitudinal weld. And basically for this one, we'd say L is equal to L1, the length of the weld at that edge. And we've got W is D minus T. If the short leg's connected, X bar is half D. And if the long leg is connected, we treat it similarly. B minus T is the width of that equivalent flat bar. Basically, if you have the slides, you can see I've broken it up into a flat bar that looks something like this, and another flat bar that looks something like this. So from these two distinct flat bar components that we could say make up this angle, we could add the two effective areas together to get the total effective area for this angle. Okay, so basically, for shapes like this, we can identify what the different rectangles might be, and we can categorize them based on how each of the individual rectangles is essentially being connected to the gusset plate. And from that, we can add up the individual areas of those rectangles to get the total effective area for these kinds of situations. Does anyone have any questions about that before we keep going? Okay. So you might say, well, where's AN2? Well, if we've got a situation where we have no transverse weld there on one of the legs, that AN2 becomes an AN3. So basically, we've got this flat bar down here. It's got two longitudinal welds on it. We've got this flat bar up here, which is still an AN3. And so in this case, AN1 is nothing. We have an AN2 that deals with this part, and an AN3 that deals with this part. Now you're going to see I've shown these two welds as being unequal. It's not very common that you'd make them unequal. You'd usually make them equal. But I'm just showing this to demonstrate the point when we're looking at the length or the equivalent length for calculating the AN2 part. If we're calculating AN2 and we go back to what that represents on the flat bar for that case, we have to calculate it based on L. Down here it says where L is the average length of the welds on the two edges. And so if we look at the angles here, we've got two welds potentially of different lengths, L1 and L2. And so when we do the calculation for AN2, we take L as a half of L1 plus L2 and use that length to calculate the net effective area for that component. Again, usually L1 is equal to L2. There are not very many reasons for them not to be equal, but this is how you would apply it if they were not. Does anyone have any questions about this one or how it's different from the previous example before we continue on with a different shape? If we have channels, they're very similar to angles, except now instead of having one leg that's outstanding from the gusset plate, we could potentially have two. Again, this could be an AN1 if we had a transverse weld along the web of the channel. We could make that an AN1 if we want to. But if we just have these two longitudinal welds, L1 and L2, again, which is quite common, then we would have the AN2 component for the web. Basically, we've got a rectangle that looks something like this. And then we've got two other things that will make a rectangle. Okay, so you'll see that here on the shape up above, these are not really rectangular, they're sort of tapered flanges. But the T is the average thickness, and so when we do these calculations, we just make an average rectangle, something like this, that's based on the thickness given to us in the handbook. And so those are the two rectangles for the outstanding legs, and then we have a rectangle here for the web. And if the web's welded with a transverse weld, we get an AN1. Otherwise, we get an AN2, again calculated using the average of L1 and L2. Okay, so very similar to angles, almost identical. We just have an extra outstanding leg that fills the AN3 component that we might have to consider. What do I do? Like I said, L1 is usually equal to L2. What do I do here if I actually have L1 that's shorter than L2? Is there anything else that I might need to consider in my net section calculations if I was looking at a situation like this where L1 was bigger than L2 for some reason? Well, a long time ago, not so long ago, but a long time ago, we looked at what happened if we had to account for offset, right, in the bolts. We had staggered bolts potentially that we might need to consider. If we have welds like this, the fracture plane is actually going to fail something like this, and it's going to be on a bit of a stagger, something like this. And so in this case, it's very minor. It's probably not going to add a significant amount of area to your net section, but you would also have a plus S squared T over 4G term here, where S was just equal to L2 minus L1, as long as they start at the same point at the edge, L2 minus L1. And G here, for this channel anyway, would just be equal to D. And T, because it's the web, would be equal to the web thickness, which is denoted here as W. And so from time to time, if you do have these welds different lengths, which really you shouldn't, they should be the same. But if they're not the same, you can get a little bit of extra cross-sectional area by accounting for the stagger of those two welds. Any questions about that before we tackle the last shape? Okay. The last shape that we might consider would be a WT. Generally speaking, if we look at S16 and look at the same section on welded sections, there's not really anything here that can help us too much. We don't really have anything. Like, we could handle, right, the flange here. The flange could be an AN1 or an AN2. But the web's not really connected to anything, right? It's connected to the flange, but the web is not being directly welded to any part of the gusset plate here. So we could technically do an A1 or A2 for the flange, but we're kind of left out to lunch here on our own when it comes to the stem. What I would suggest in this case, and what would be common practice, would be to just take the net effective area as the shear lag factor 1 minus x bar over L multiplied by the gross area of the WT. This is similar in some ways to what we had here previously. We're using that same 1 minus x bar over L calculation to get a shear lag factor. And in this case, it would work relatively well. X bar is equal to y here, right? So that's x bar that we'd use for the calculation. And so it's pretty straightforward to do this. The reason we don't really have any guidance for this is nobody welds WTs, like practically speaking. The S16 standard is written in a way that reflects Canadian practice. And so 99.9% of the time, if we have a WT working as a tension member, it's in a truss, or if it's part of a brace of a structure, it's going to be bolted. And so usually, we don't weld WTs anyway. WTs. And so you probably shouldn't have to deal with this situation in any case. Does anyone have any questions about this last potential situation that we would maybe weld something where we have different cross-sectional shapes making up the cross-section, and how we might handle that before we get into an example of how we might apply this? Okay, so the example might be a little simple, but it's also for completeness here. And don't get too excited because there's like lecture A and lecture B here this morning. I'll talk about this and I'll talk about HSS afterwards. But we're going to come back very briefly to this brace example in that school on the north side. We already know that this brace is carrying 580 kilonewtons of factor of tension. We already know that the bolted side is governed by the net section fracture strength, which was 587 kilonewtons. We know the yield strength of the bar was 709 kilonewtons. And we know that the strength of the welds, as long as we use the 250 millimeter long 8 millimeter welds, was something like 600 kilonewtons. So we're almost done looking at this brace. The only thing we haven't done yet is look at what the effect of having these welds on the tension member would be on the effectiveness of this part of the brace in tension on the net section. Okay, so we're looking at the same flat bar. We've got the same 250 millimeter long, 8 millimeter sized fillet welds that we looked at the end of the example on Friday. And basically what we have was something like this. We've got 2 longitudinal welds, 8 millimeters in diameter. And what we're trying to do now is we're going to figure out if the net section fracture resistance is acceptable or if it's not acceptable. Okay, so it's the last part of this brace. The stresses are going to transfer up through here, and only a certain percentage of the bar is going to be effective in tension. So our goal here is to calculate the net section fracture resistance for the flat bar brace at the welded connection. Does anyone have any questions about what it is we're trying to do in this example before we get into some of the calculations? Okay. So the first part is, how do we start this? Basically what we need to do is we need to identify which of these net areas are we going to include in the net effective area. So I'll ask you, are we going to be calculating an AN1, an AN2, or an AN3 for this flat bar brace? Is it this one? No. Is it this one? Yeah, right? We've got 2 longitudinal welds, no transverse weld. This is an AN2 calculation, and that's what we're going to do for our flat bar brace. To calculate AN2, we need to know how long the weld is relative to the width of the plate. Here we know the width of the plate is 150 millimeters. We've been dealing with this flat bar for some time. And from the weld symbol here, we know that the weld length is 250 millimeters. So basically we've got a weld that's somewhere between W and 2W, which would be 300 millimeters, right? So it's not less than W, it's not greater than 2W, and so we basically fall under this case here, right? So we've got a situation where it's longer than W but shorter than 2W, and so we're going to calculate AN2 as a half WT plus 0.25 times LT. Okay, so ANE for us here is equal to AN2, which is equal to 0.5 WT plus 0.25 LT. W is 150 millimeters. That's the width of the plate. T is the thickness, which is 15 millimeters. And then we've got plus 0.25 times L, which was 250, and also times T, which is not the thickness of anything other than the plate. Okay, so these calculations, if it hasn't been clear yet, these have nothing to do with the size of the weld. They only have to do with the length of the weld. Okay, so size of the weld does not come into play for any of these calculations. And if we look at the situation here, of course, that's going to keep smacking my screen off to the side, which is quite annoying. So if we look at those calculations and try and figure out what the total AN2 is, we can put all that into our calculator and get that our AN2 is 2,063 millimeters squared. and we can use that net effective area to calculate the factored tension resistance. Before we calculate the factored tension resistance, are there any questions about why we did this calculation or what this number means before we calculate the resistance? Okay. So we get TR is phi u ANE FU. Phi u is always 0.75. ANE is the 2,063 millimeters squared we just calculated. For 350W steel, we're dealing with an ultimate tensile strength of 450 MPa. And so our total factored resistance is 696 kilonewtons. Okay. So to me, that's kind of interesting. Like, that's pretty close to the gross section yield resistance anyway. The gross section yield resistance for the flat bar was 709. This is not yield, but it's net section fracture. We're getting kind of close to that resistance. In any case, is the flat bar brace at the welded connection side acceptable to carry the 580 kilonewton factored tension force? Good. Right, this is greater than the 580, which means the probability of failure is acceptably small. Okay, so we start with this flat bar brace, identified from the weld symbol how the welds were arranged, and from the arrangement of the welds, identified this as an AN2 calculation. Based on the length of the welds and the width of the plate, AN2 was the second case from that particular clause. We calculated the net effective area and used that to get the tensile resistance. Does anyone have any questions about that example before we move on to HSS connections? Okay. These are interesting because welded HSS is often specified because architects love HSS sections. They're also quite effective, particularly if you have a brace that will be carrying both compression, well, not both, but either compression or tension depending on the direction of loading. HSS are often used as tension compression braces, and it's just very difficult to weld, to bolt them in any other kind of meaningful way. You can try and come up with a bolted connection, but 95% of the time, even if you're bolting it, you're still going to weld something to the HSS in a way that looks something like this. What's going on here is they are going to be drilling and milling out the walls of the HSS, and so here's a picture of some HSS sections that have had that slot milled out. And basically in the field, they're going to take that, they're going to have the gusset plate up there and the gusset plate already down there, or they're going to take that and they're going to try and rotate it in place so that the slots go over the gusset plate. To make sure that we can accommodate that, there's usually a little gap at the end here of the slot just to make sure that there's enough space that they can get that brace on the gusset plates. And so there's going to be a slight reduction in the net area here just due to the fact that we've got slots. Okay, so this is different from the sections we've talked about previously. We are going to have an AN term, which is less than AG, right? We're going to be removing some of the cross-section to make these slots. And then we're going to have to deal with the shear lag effects because we're really only welding the walls where the gusset plates are, and we're not directly connecting the other side walls. And so basically what we have to do here is look at the expressions that we would use in this kind of situation to handle the shear lag effects associated with this welding arrangement. There's some work done at the University of Toronto in early 2000s or maybe late 90s, I can't recall, that informed what we do in CSAS 16 to handle the situation. Basically, we've got two situations. We take ANE is equal to the net area times some shear lag factor. And that has to be, or generally, I don't like the way this is written necessarily. Let's just pretend that this isn't here, and let's pretend that this isn't here for now. Basically, we're just going to say ANE is the net area that we have left over once we get rid of the slotted component, multiplied by a shear lag factor that looks pretty similar to what we've seen before. Right? Before we used to see 1 minus x bar over L. Now we have 1.1 minus x bar over LW. Now, don't get confused by this, please. I do not like the way that this is written because it starts to include LW, which we've not been using before. We've been talking about L. We've been talking about LW to basically mean the sum of the individual lengths of the weld segments. And based on the picture that's in the commentary for this, it's the same thing that they're talking about. So they're talking about the length of the welded connection. they're not talking about LW the same way we've been talking about LW before. For me, LW is the total length of weld. L is the length of the welded connection. And here they're conflating those two a little bit. So just consider this L, consider this L, and consider this L. And right, they say here the usual case has the total weld length being 4LW. So it's just a little bit confusing. So you can just go in and scrap out those W's, not because they shouldn't be there in terms of how they're written in the standard, but they shouldn't be there because it's confusing based on what we've talked about so far. So basically they say, okay, 1.1 minus x bar prime over L. And now the difference here is there's this x bar, it's not x bar anymore, but it's x bar prime. And so the question is, how do we calculate x bar prime and what does that mean? It's more or less the same thing. It's the distance between the shear plane of the welds here, so the face of the gusset plate. It's the distance to the centroid of half the cross section. And so here, if we cut this circle in half, basically we have a centroid of that half circle away in terms of being a certain distance away from the gusset plate. So it's very similar to how we've thought about L or x bar prime before or x prime before. It just is a little bit more involved in different situations. So I'll talk about some of this part here. So we usually do this. We say ANE is AN times 1.1 minus x bar prime over L. And then they start telling us like it has to be greater than 0.8 AN, and ANE is equal to AN when x prime is over L is less than 0.1. So I just want to provide some context for what's going on there. For the most part, they're not saying to us in the way that the standard is written, they're not trying to tell us that ANE is never going to be less than 0.8 AN. That's not the right way to think about this. The right way to think about this is if ANE is less than 0.8 AN, it's not going to be net section fracture that will be governing the strength of the tension member anymore. It's going to be some kind of tear-out behavior that looks something like what's shown in the picture here on the right. Net section fracture for these welded connections looks something like this, right? It tends to fracture close to where the gusset plate is welded to the cross-section. Through the shear lag effects, you can see some of the stresses start to get transferred out over here as well. And so basically we're trying to figure out how much of that cross-section is effective in tension. And when Jeff Packer and his student did this research at University of Toronto, what they did was they did some experimental tests and some finite element analysis, and they said, okay, what is the shear lag factor? And they basically got something like this. Whoops, not quite at the end there. That was a little bit abrupt. But they got this curve that's shown in the dashed line on the slide, something like that. Okay, so obviously at a certain point we start to get a reduction in the net section, but you can't really figure out what the shear lag factor is beyond a certain point, because beyond that point you're not going to see net section fracture happen. Okay, so they can't empirically figure out what the shear lag factor might be for any other situation, because this is where this sort of tear out of the section along where the welds are connecting it to the gusset plate starts to govern the strength. And so we're not saying that we always get 80% of the net section effective. That's not the case. What it's saying is we cannot observe net section fracture for situations where we have shorter welds than what we'd get for 0.8 AN. What S16 loves to do is they love to take things that are curved and make them straight lines, because it's easier to deal with straight lines, right? And so instead of dealing with that curve, we basically say, well, as long as x bar over L is less than 0.1, we get all of the cross-sectional area effective. Shear lag factor is 1. For other situations, we're just going to draw a straight line from here to here. And so if x bar over LW is between 0.1 and 0.3, we're just going to use this straight line, which passes through 1.1 up here. And so that's why you see 1.1 minus x bar prime over LW. And beyond x bar prime over LW is equal to 0.3, we don't really do the calculation because block shear is going to govern the strength of that particular connection. Okay, so basically what we're saying here is that the shear lag calculation is done like this, where we have 1.1 minus x bar over LW when x bar prime over LW is more than 0.1. That's this range. We're fully developing the net section. ANE is equal, or sorry, that's this range where we're not fully developing the net section. And when x bar prime over LW is less than 0.1, we are fully developing the net section, and we get ANE is equal to AN. Okay? Are there any questions about that before we look at an example of how we might handle this situation for a welded HSS? Okay. So calculating the centroid of those half shapes might seem frustrating and a little bit, you could do it. It's time consuming if you do it yourself, but I've gone ahead and just kind of done that for you already. So if you have a square HSS section, the distance to X bar from the center of the cross section to the half centroid is 0.375 d minus t. For round HSS, that same distance from the center to the half centroid is 0.318 d minus t, where d is the outer diameter, t is the thickness, and for square HSS, d is the outside width. And then we just take that X bar and subtract half the gusset plate width to give us our X bar prime that we plug into the calculation for the shear lag factor. Okay, so we're going to look at how this applies to a situation like this. This is actually the connection in the new building on, I guess, like upper side of Queen Street. Does anyone know where like the Queen Street Creamery is? Next to the Chess Piece Cafe, and there's like a 6-story building across this, like it's, where would I say it is? No one knows where the Chess Piece Cafe is? Like, you know where Town Hall is, right? You go to Town Hall and you continue west, and then there's this big 6-story building that looks really ugly when you're passing over the overpass. It's got the roof like this. Everyone seen that building before? Come on. You got to go take a look at your own city. Anyway, I got to, I don't know if I trespassed or not. I stayed outside the fence, but when they were building that structure, this was the bracing arrangement that they had in that building. Okay, so we can take a look at what we think the strength of this connection might be in terms of what this shape is. Now, of course, I can't get the thickness, so I don't know exactly what this HSS is, but for the most part, I could take a pretty reasonable guess. So if this was an HSS 152 by 152 by 6.4, and it was on a 1/2-inch thick gusset plate, and it was welded on front and back with 8mm welds, that's probably generous. Probably it's 6. But we'll just say front and back, 8mm. And to me, I know this is a 6, like you can visually tell if something is a 6x6 or not. And based on the dimensions, it was about 6 inches of weld, right? So in terms of this being a square HSS, the length of the weld was about the same. So 150mm of weld. And again, that's kind of something like this on 4 sides. There's the HSS shape, and there's going to be a weld here, and a weld here, and a weld here, and a weld here. And that's just always the way these shapes are going to look. Okay, so our goal here is to calculate the net effective area. We won't calculate the strength, but we'll calculate the net effective area for the HSS section as it's shown here. Does anyone have any questions about what we're trying to do here before we do some calculations? Okay, so we don't really need to do much in terms of decision making here. We just need to apply this part of the CSAS 16 standard. And all we really need to do here is figure out what X bar prime over LW is going to be, and that's going to help us calculate the net effective area. Okay, so we've got a square HSS section on a gusset plate, and so the first step here is to calculate X bar prime. X bar prime is X bar minus 1/2 of the gusset plate thickness, and then we've got X bar prime calculation here. So we're going to calculate X bar, plug it in the expression for X bar prime, and use that to calculate the ratio of X bar prime to LW. Okay, so X bar is 0.375 multiplied by D minus T. Okay, D is the outer wall, T is the thickness. From an HSS 152 by 152, the outer walls are 152 millimeters. And you actually have to look up in the table, because it gives us 6.4 here as the wall thickness, but what that actually is 6.35 millimeters. They just rounded up to the second digit or the first decimal place when giving the section designation. But you have to go look at the handbook to find out what the exact thickness is there before you plug that in and work with it. But if we do that, we do 0.375 multiplied by 152 millimeters minus 6.35 millimeters. And if we do that, we get an X bar value of 54.6 millimeters. we can plug that into the expression for x bar prime, which is x bar minus 0.5 times the thickness of the gusset plate. That's a bad 5. 0.5. So that's 54.6 millimeters minus 0.5 times the thickness of the plate. Now, this is a very minute detail that's not super important, but when we denote these things as metric, we always say it's a 13 millimeter plate. 13 millimeter plate is just the roundup of the imperial size, which is half an inch. Half an inch is actually 12.7. So there is not really any such thing as 13 millimeter plate in Canada. We use half inch plate, and anybody who's doing the fabrication would know that it's a half inch. So we're not going to use 13, we're going to use 12.7 millimeters. And if we do that, we get an x bar prime value of, sorry for writing it in that weird way, but 48.3 millimeters. Okay? Does anyone have any questions about that calculation before we continue? Okay, so we calculated x bar prime based on the dimensions of the cross-section and the thickness of the gusset plate. And now we need to figure out what x bar prime is as a ratio to L. Okay, a reminder here, L, that's the length of the welds. It's 150 millimeters. And it's not the total length of the welds, it's just the length of the connection that's welded. So we get the 48.3 over 150. And when we do that, we get 0.322. Okay? So that's greater than the 0.1 that we have, right? So it's greater than 0.1. But when we look at this graph, we're kind of just over here somewhere, right? So we're really just getting into the area where it's unlikely that this is really going to govern in terms of net section fracture. We're really going to be looking at the net section, or sorry, the gross shear tear out. But we'll just go ahead with this anyway and see what the net section area would be if we continued to use this particular expression. Okay, so the next thing we need to do is calculate AN. And AN is something we need to calculate to deal with the fact that we're going to be cutting out some of the HSS to make a slot, right? So the HSS is going to be cut something like this. And we're losing these two parts of the area. And so AN is the net area left over after the slot is cut. If you were building this and you were cutting out a hole in the HSS to slot over the gusset plate, how wide would you make that cutout, do you think? Maybe the thickness of the plate plus a little bit of tolerance, right, to make sure it fits over. So we're going to make this slot the thickness of the plate plus 2 millimeters, just to make sure that, you know, it fits over the plate. It's not going to be perfect, so we need to make sure we can fit that up in the field. And so we're going to have this on two sides. And so for us, ANE is going to be AG for the cross section, sorry, not equals. And then we're going to subtract 2 TP plus 2 millimeters times T, which is the wall thickness. Okay, so we're going to get rid of 2 of those to make those slots. We need the cross-sectional area then. And so from the handbook on, do I have the page number? Yeah, so I think so. If you go to page 6-98, you should be able to find these cross-sectional properties for G4020 HSS sections. So for us here, A is equal to 3,610 millimeters squared. And we already know T is 6.35. So if we do this calculation, we get 3610 millimeters squared minus 2 times 12.7 plus 2 millimeters times 6.35 millimeters. And once we get rid of the slots, our AN value that's left over is 3,423 millimeters squared. Okay, so we didn't even lose 200 millimeters, so the slot really didn't take a whole lot of cross-sectional area away from us. Any questions about that net section calculation before before we get to the end of the example. Okay, so that's AN. And calculating ANE, we need to take AN and multiply it by the 1.1 minus x bar prime over L. They tell us this should be greater than or equal to 0.8 AN. They should just get rid of that and not actually tell us that. So how we do this is we take the 3,423 millimeters squared, multiply by 1.1 minus 0.322. That was the x bar over L ratio. And when we do that, we get a net effective area, when we do that calculation, equal to 2,630 or 2,663 millimeters squared. Okay, if we were to compare that to the 0.8 AN, 0.8 AN is equal to 2,739 millimeters squared. And technically what this means is, well, we're not really going to be getting net section fracture happening. We're actually going to be checking that gross section, or sorry, the shear, block shear type failure tear out mechanism. And while I'd like to show that in the example today, there's not always enough time to do all of those calculations, but I do have it shown in the example notes there how to do that calculation. You're just taking the tear out length. It's very similar to bolts. You just have the gross area in shear multiplied by the ultimate strength of the component in shear. Okay, so we looked at this connection, and because of the way it's welded and because it's a certain shape, we treat shear lag a little bit differently. We figure out what x bar prime is, we figure out what the ratio is, figure out what AN is, and then use the shear lag factor to reduce AN to get ANE. Does anyone have any questions about the example before we review the learning objectives and wrap things up? Okay, well, basically, even though I lost 1 point here, apparently, there's the other one, describe how the stresses are transferred from the welded segments to the cross-section. But now you should also calculate the shear lag factor and effective area for welded cross-sections, and do the same thing for welded slotted HSS tension members. Any questions about any of that stuff today before we wrap things up? All right, see everyone this afternoon in the lab.